ladies and gentlemen, this is section 2.6, and we're talking about proving statements about segments and angles. So just as a warning, this video may be longer than usual. I'm not sure because this is my first try at it. So if it is longer than usual, feel free to skip around to different examples if you just want to look at a specific one from class. Or if you're absent, feel free to look at this in maybe two parts because it may be longer. So starting with a couple of definitions. First of all, with deductive reasoning and inductive reasoning, conditional statements and things like that, we've been building towards writing what are called geometric proofs. So a proof in general is we're just forming a logical argument that shows that a statement is true. So if a problem says show that ... or prove ... something like that, writing a proof is writing a logical argument. So we're going to use deductive reasoning to write a logical argument. We'll use facts and logic and definitions and things like that to write some sort of logical argument. In essence, what we're doing is we're acting as a lawyer in a courtroom. A lawyer uses witnesses and evidence and expert testimony to prove that something is true or false. And in this case, we're acting as a prosecutor. We're proving that something is true. And so we're doing the same thing. We're trying to form an airtight case using things like different types of evidence, witnesses, and things like that. So a couple of resources that we usually use, one is given information, usually in the form of a diagram or in the form of a statement. So this is some evidence that we use in order to prove that something is true using our logical argument. The second resource we use, both are very beneficial, are postulates, properties, theorems, and definitions. Anything we've covered up until this point in time is fair game to use in a proof. So postulates, like we talked about the other day, properties we talked about in section 2.5. We haven't talked about any theorems yet. Those will be discussed in section 2.7. We have talked about definitions, definitions of congruent segments or congruent angles or perpendicular lines, things like that. We've talked about different definitions that we can use here. So let's make an attempt at writing some sort of proof. And usually they're written in this format, two columns, a statements column and a reasons column. Sometimes they're in paragraph form. Sometimes they can be in different forms. Mainly we will deal with two-column proofs. On occasion, I may ask you to write paragraph proofs, which is just a proof in paragraph form, so we can work on our writing and communication skills. So for this particular problem, it says 4 steps of a proof are shown below. Give the reasons, so we need to fill in the missing reasons on the right. And actually, I'm going to ask us to fill in the missing statement at the bottom. So usually you're given some information. Here we're given that AC equals AB plus AB. And you can see that AB over here is this half, and AC is the whole thing. So we're given a picture that helps. We're given some given information. And we want to prove that AB, the length of AB, equals the length of BC. This is kind of like our goal. This is what we're trying to show is true. This is our final destination. All right, so this is our goal or our final destination. Now, when you're writing a proof, there's usually two ways we can form logical arguments, two different things that we can use. The first thing, to show that statements are true. So if we're writing statements, statements build upon two things. First thing they build upon are given information, such as the picture or up here. So I'll just mainly say the diagram, so from the picture. Always use the picture when possible to help you. And the second thing it builds upon is statements can build upon prior statements. So for example, if I were writing in statement 3, I can build that off of statement 2 and 1 if I wanted to, and we'll get to there in a minute. But let's just start with our proof. So in the process to show that AB and BC are equal, that's what we're trying to show here, we start with our given information as a rule because it's given to us. We know we're going to need it at some point. 9 times out of 10, it will be logical to use it as our first step. So in this case, we start with our given information, and our reason that we can say that's true is that it's just given to us. That's our evidence. So why can we say this is true? Because it's given to us. That's our logical reason. For step 2, whoever was filling out this proof noted that AB plus BC equals AC. Well, first let's check the diagram and see if that helps us. So looking at the diagram, AB plus BC equals AC, the whole thing. So adding 2 pieces to equal the whole thing. Well, we talked about something already that talks about adding two pieces together to equal the whole thing. That was from chapter 1. That was our segment addition postulate. So the reason why we can say that statement 2 is true is because of the segment addition postulate. And it helped us to look at our picture to see that that was an example of the segment addition postulate. So looking at the diagram can help. Now, line 3 says that segment AB plus segment AB equals segment AB plus segment BC, or the lengths of those segments. Well, let's start by looking at the diagram. There's not really any visual that contains two segment ABs. There's just the one. There's no example of having AB plus AB in the picture. We don't have two of them, so the picture probably won't help us. But let's look at prior statements. Let's see if statements 1 and 2 can help us draw the conclusion to statement 3. Sorry about that. I had a visitor in the room. So, again, we're going to see if statement 3 can build off statements 1 and 2. Well, if you look at statements 1 and 2, they share something in common, AC. And if we cut out the piece that's in common, we're left with AB plus AB, which is right here, and AB plus BC, which is right here. So what property we talked about that says you can take the piece that's common and cut it out and leave the other two pieces there? Just like the law of syllogism, that's our transitive property. Sorry about that. So again, that's the transitive property, just like the law of syllogisms. So that's how we got to statement 3. Now our ultimate goal was to have AB equals BC, the length of AB rather equals the length of BC. So that's always going to be our final statement. Your final statement should always be your goal, your destination. Now that's your final statement. Your final reason is not prove. I can't emphasize that enough. Prove is not a reason. If you were to say the length of AB equals BC, and I were to say how'd you get that, and you said prove, I would think that's kind of illogical. So prove is never a reason, unlike given, when given can be a reason. So how do we get from line 3 to line 4? Well, it looks like we kept AB and kept BC, but we subtracted AB from both sides. So they canceled on both sides. So that was our subtraction property of equality. Subtracting AB from both sides, so we're left with simply AB equals BC. And that's the conclusion of our proof. So again, you can build statements upon the diagram like we did with the segment addition postulate, or they can build on prior statements like when we use the transitive property to get to line 3 and the subtraction property to get to line 4. Let's try another example of a two-column proof. This one involves angles, so let's look at our given information and what it is that we're asked to prove. We're given that the measure of angle PMN, so this angle over here, is equal to the measure of RBC, which is this here. So those two are equal. I marked the picture just to help me because I'm a visual person and I like to look at the picture, at the diagram, and know what's going on. And we're asked to prove that if we add the measure of angle ABR to the measure of angle PMN, it equals the whole thing, the measure of angle ABC. So with our statements, we start off with the measure of angle PMN equals the measure of angle RBC. That was our given information. Therefore, our reason here is just going to be given. Now moving on to statement 2, it's logical to use addition for something since we're looking to prove something that involves addition. So at some point, we'll have to use addition, either an addition postulate or an addition property. So here, for statement 2, it's stated that the measure of angle ABR plus the measure of angle RBC equals the whole thing, the measure of angle ABC. So if we're adding both pieces to equal the whole thing, that's a perfect example of our angle addition postulate back from section 1.4, where we added two angle pieces together to equal the measure of the entire angle. So that's the angle addition postulate. Now again, if 3 is our last statement, we know it should be whatever we're trying to prove. So the measure of angle ABR plus the measure of angle PMN equals the measure of angle ABC. Now, what changed from statement 2 to statement 3 is the question. Well, the only thing that changed was the measure of angle RBC became the measure of angle PMN. That's the only thing that changed. Well, what happened in this case is that since we know these two are equal because of our given information, we can replace one with the other. That's using our substitution property. So instead of using RBC, we used PMN because they're equal, so we can substitute them for each other. Just like in algebra, where if x equaled 2, you could simply plug in 2 for x. They were equal, so they were interchangeable. So that's our proof for example 2. Now, if we're just looking at this logically, maybe not in proof form, or just logically, if we know that these two angles are equal, and if we add these two together, it equals the whole thing, then logically, if we add these two together, it should still equal the whole thing. And let's do this with numbers. So let's say that this is 30 degrees. That means this must be 30 degrees. And let's say this is 20 degrees. That would make the whole thing here 50. So logically, it's true that if we add the measure of angle ABR up here and the measure of angle PMN over here, it'll still equal 50 because these two angles are equal. So that's a good example using numbers. Moving on to another proof. Here we're going to write the whole thing from scratch. So we're going to do the statements and the reasons. Well, first, we're given that the measure of angle A equals the measure of angle B. And the measure of angle B equals the measure of angle C. So I'm going to put another single tick mark here, and you can probably already see what's going to happen. So that's our given information. So that's our first statement, because we'll need to use it at some point. And our reason, of course, is given. Now, looking at the picture, you can probably already see that all three angles are congruent. Now, looking at my two statements, I want to eventually show that angle A is congruent to angle C. So to get to that point, I can cut out angle B here using my transitive property. So I just have that the measure of angle A equals the measure of angle C. And that was the transitive property of equality, I should say. Now that doesn't look exactly like up here. Down here we're talking about the measures of angles are equal. Here we're not talking about angle measure, we're talking about angles, and we're using congruent. So we have to somehow go from this to saying that they're congruent. Well, how do we know that if two angles have the same measure, we can logically conclude that they're congruent? Well, that's following from the definition of congruence, or the definition of congruent angles, back from chapter 1. Where it says that if we have two angles whose measures are equal, then they are congruent. Or the converse. If two angles are congruent, then their measures are equal. So to go from equal to congruent, we had to use the definition of congruence, or in this case specifically, the definition of congruent angles. Now for this one, I've given you a single blank, the statement for number 4, and we're going to fill in the rest together. We're supposed to prove this property of midpoints. If you know that M is the midpoint of segment AB, prove that the length of AB is 2 times the length of AM. And we're given that M is the midpoint. So again, we're going to start with our given information. M is the midpoint of segment AB, and that should have a segment symbol over it. And of course, that is given to us. Now, logically, we can deduce, and if you ever hear someone say to deduce something, that's using deductive reasoning. So logically, we can deduce if M is the midpoint, then both halves are going to be congruent. And we know that back from section 1.3, saying that the definition of a midpoint states that it divides a segment into two congruent halves. So those halves are congruent. Now again, we have an issue. We're talking about congruence here, but in our proof statement, our goal, we have equals, not congruent. So we need to somehow go from segments being equal to their congruent, I should say, to their lengths being equal. We need to somehow go from congruent to equal. So again, we're going to use the definition of congruence. In this case, the definition of congruent segments, saying that if they are congruent, then indeed their lengths are equal. So we can move from congruent to equal, or vice versa. So we know that they're equal. Now I gave you statement 4 because that could be difficult to see if this was your first time seeing a proof that involved this type of problem. So we know that we're trying to prove that the length of AB equals 2 times the length of AM, or 2 AMs put together. So we're adding two things together, 2 AMs. So I should try adding something together. So I used my angle or segment addition postulate, saying from the picture as my resource that AM plus MB equals the whole thing, the length of AB. And that's our segment addition postulate. Because we're adding something in our final answer here, so I know I should use something with addition. Now sometimes a proof can be guess and check. If you did something that didn't work, maybe you have to take it back a couple steps and try something else. So don't feel discouraged if you have to start over or erase your second half and start back in the middle somewhere. It does happen. It's all the process of learning something and making mistakes and learning from those mistakes. Sometimes it's trial and error. So now I know that I'm trying to show something with AB and AMs. Well, here I have an AB, one AM, but I should have a second AM. Well, fortunately, I know that AM and AB, or MB, are equal. So I can substitute MB with AM instead and write that as my next statement. And that was using substitution. I can plug in one for the other. And finally, now that I have two AMs, I can just combine like terms and write that as 2AM instead of AM plus itself. Just combine those like terms together, equals AB, which is what we were looking for up here. Now, for my reason, I'm not going to say combine like terms, because when Euclid came up with this system of geometry, he didn't use combine like terms in his proofs. He used the distributive property as a type of combining like terms. So anytime you combine like terms, you're using your distributive property. I know it's awkward, it's something that we don't think about, but it is indeed combining like terms using our distributive property. If you don't want to know how that works necessarily, if you think it might confuse you, feel free to move on, but I'm going to go through that very briefly here. If I'm adding AM plus AM equals AB, here's a brief, kind of like an algebraic proof of distributive property. Well, the distributive property says I'm distributing something into parentheses. But in this case, I'm going to put these in parentheses and I'm going to take something out. Since these, and that's called factoring, back from Algebra 1. So factoring is like using the distributive property in reverse. So since this is common, I'm going to factor out AM. And inside, I have my assumed 1 in front, so I have 1 AM plus another AM. Now if I add my 1 plus 1 inside the parentheses, I have 2. And using my commutative property of multiplication, the order doesn't matter. I can write this as 2AM equals AB. So I use my distributive property in reverse by factoring to essentially go from here to here, which is just like combining like terms. So that's what Euclid had to do. He didn't use combining like terms. He kind of used the reverse of the distributive property. It's the long way to go about it. We know this today as combining like terms, but that's what he had to work with. All right, starting our next proof, which we didn't go over the first day in class, we're given that 2 times the measure of angle ABC equals the measure of angle ABD. So 2 times the measure of angle ABC, this angle here, 2 times that equals the measure of the whole thing. And you're probably already thinking, well, then these two are probably going to be equal, because if I add them, I also get the whole thing. And that's exactly what we're trying to prove, but we're going to write a proof for it. So again, we start with our given information, because we know we're going to need it at some point, and the reason is given. Now our second statement, this is what might be kind of hard to see. So we know we need a statement with both ABC and CBD, so we're going to need something with both of those together. Well, let's try looking at the diagram. I can write a statement with both of those together by using my angle addition postulate. The measure of angle ABC plus the measure of angle CBD equals the measure of the whole thing, ABD. So if we write that as a statement, we can finally get ABC and CBD together, right here and right here, and that's going to be our angle addition postulate. So we have them together, so now we can maybe manipulate statement 2 to try and get these two by themselves and get rid of this unneeded ABD, which is not in our proof statement, so it's not a part of our goal. So let's see if we can somehow manipulate our statements 1 and 2 to get to a new statement that looks better. Well, statement 1 and 2, they do have something in common. Here, we have ABD in common. So maybe we can cut out what's in common and leave what's left. The measure of angle ABC, 2 times the measure of angle ABC equals the measure of angle ABC plus the measure of angle CBD. So we used our transitive property to cut out what was the same and leave what's left. So we can just write 2 times the measure of angle ABC equals the measure of angle ABC plus the measure of angle CBD. That's our transitive property of equality. And finally, I have two ABCs over here, and an ABC and a CBD over here. Well, if I subtract a single ABC from both sides, on the right side I'm just left with CBD, and on the right side I no longer have two ABCs, I just have one. That's exactly what I wanted in my proof statement. I wanted the measure of angle ABC equals the measure of angle CBD. So if I just subtract ABC, one from both sides, that's my subtraction property of equality. So there's my next example of a proof. So again, it's good to use your picture. We know that we need to have ABC and CBD together, so we added them together using the angle addition postulate, and then we kind of manipulated it from there by using our transitive and subtraction properties. And for our final proof, we're given that angles 1 and 2 are complementary. We're asked to prove that these two lines, which really look like rays here, are going to be perpendicular. Well, if we're going to prove that these are perpendicular, we should probably show that they form a right angle, because we know we need right angles for them to be perpendicular. So we probably have to show some sort of right angle to show that they're perpendicular. So again, let's start with our given information. We're given that these two angles here are complementary. That's given to us. We're going to have to use that at some point. Well, we know we need to show there's a right angle, so let's see if we can do something with angles 1 and 2 and see if they can equal 90, if we can make them a right angle. So if they're complementary, then we know that they're going to add to give us 90 degrees. And that's simply the definition of complementary angles back from section 1.5. Complementary angles always add to give us 90, so again we're using a definition. You should never forget that stuff because it'll always come back. Now, we know looking at the picture, if we add angles 1 and 2, that equals angle ABC. So instead of adding them together to equal 90, we can say they also equal angle ABC, which is using our angle addition postulate. And the reason why we're doing that is because, again, we want to show that they form a right angle. So we want to show that angle ABC is a right angle. So we should have that in there somewhere. And now that we know that we have angles 1 and 2 in common, we can do one of two things. One, we can say we can use our transitive property to just leave what's left. Or we can say it's substitution by plugging in 90 for angle 1 plus angle 2. So down here, plugging in 90 instead. So here you can look at it as transitive or substitution. Either way, you get the same answer. And a lot of problems, 9 times out of 10, they're interchangeable. So we can use substitution property of equality, or if we looked at it as the transitive property, either way is fine. I just use it as substitution property in this case so you can see it used both ways at some point in this lesson. Now that we know that the measure of angle ABC is 90 degrees, we can classify it as a right angle, which is what we needed. And that's using the definition of what a right angle is. And included in the definition of perpendicular lines, we need a right angle. So that's why we use a right angle, not just 90 degrees, because the definition formally says you need a right angle. So now we can say that those lines are perpendicular because we have a right angle, and that's using the definition of perpendicular lines. Again, we couldn't just say because they're 90, we need to say it's a right angle because the right angle piece is what is actually in the definition. So that concludes our lesson, our introduction rather, to proofs. We'll be doing a lot of practice with these. We'll do some more practice in section 2.7. Hopefully this was helpful. Feel free to look back at any examples, ask me questions anytime. My email address is on Edline, and I'm in my room every day at 7:30 after school, Mondays and Wednesdays until 5:30. Farewell.